After the Second World War, the atomic race began. Britain didn't want to lose it. It needed atomic weapons in order to preserve its global influence. Because it was unable to enrich uranium at the time, it desperately needed an alternative route. Wind-scale piles were born because of that need. Shortly after starting the operation of the piles, and even before the famous accidents, development of a much more economical system was on its way. Magnox was slowly being born with dual purpose in mind. Waste heat piles produced was now utilized to generate electricity for the national grid. Coolant was far superior in both safety and thermodynamic properties. Development and evolution of new technologies wasn't stopped there. Parallel with Magnox operation, experiments with an even newer and far superior reactor type began. It was known from the early days of Magnox that it would never be an ideal reactor for pure civilian use of electricity generation. So new strict and highly ambitious goals were set to make a reactor capable of utilizing state-of-the-art turbines at the time. Turbines whose parameters could be obtained only by fossil fuel plants. In order to obtain those parameters, drastic changes in reactor design were needed. High-performance turbines required high-parameter steam. In order to achieve that, the fuel operated at much higher temperatures. Magnesium alloy as cladding and uranium in its metallic form as fuel were no longer suitable. Metallic uranium would alloy with practically any cladding material, so its ceramic form was chosen. Fuel pellets are hollow in the middle. Such design prevents high temperature accumulation and makes room for fission gases. Many of such fuel pellets were stacked inside fuel pin. Stainless steel was chosen as cladding. Magnesium alloy would simply melt. The new material changed the neutronics of the reactor. Because of the higher capture cross-section area of the stainless steel, enriched uranium was now required. Many of such fuel pins in a bundle made one fuel element, and 8 of such elements make the fuel assembly of the stringer. Graphite sleeve is used to divide two gas streams, one of them reentrant. Higher fuel temperatures and higher neutron flux degraded the graphite at much higher rate. Higher temperatures would potentially cause boudoir reaction, a reaction between carbon dioxide and graphite, making carbon monoxide. We could simply cool the reactor graphite with the gas stream parallel to the flow around the fuel elements. Unfortunately, such an approach would simply dilute the high temperature gas coming from the fuel channels with the relatively cold gas coming from graphite cooling. Reentrant flow helps us overcome this problem. The animation I made will help us better understand some core principles of this reactor. Most of the gas exiting the circulators goes straight through the fuel assembly. The other portion of the flow goes around the core and through it, cooling the graphite and extending its life. Instead of meeting together, the second flow goes down along the sleeve of the fuel assembly and enters it at the bottom, there meeting with the main flow. All this thanks to gigantic structure put above the core, the gas baffle. It separates two regions, high pressure inside and low outside of it. It makes re-enter flow possible. The core, together with this gigantic baffle, is housed inside enormous concrete pressure vessel. All that reinforced concrete for only one function, to withstand all the force imposed on the enormous surface, a little over 40 atmospheres of pressure. Now that we have learned the ultimate design of this reactor and how graphite is protected from high temperatures, let's concentrate on the second enemy, radiolysis. It breaks carbon dioxide into radicals of oxygen and carbon monoxide. The oxygen radical reacts further with the carbon of the graphite, making carbon monoxide. Because of that, graphite bricks were provided with holes, methane channels. Methane was meant to reverse the reaction and deposit back the carbon. The second big advantage of the AGR was its ability for online refueling. Fuel loading and unloading could be performed online thanks to this gigantic machine that definitely deserves its own topic. Let's now jump to the hidden workhorses of the reactor, gas circulators. After all, safety also depends on them. AGR has 8 of them around the core, 2 per boiler. They are of radial type, electrically driven. Gas flow was regulated thanks to guide vanes. RPM controlled through frequency was also possible. There are 4 boilers around the core and inside the pressure vessel. Each one worked independently, had its own feedwater pumps and auxiliaries. Every boiler consisted of 3 units. Boilers were of one screw type. Each unit consisted of economizer, evaporator, superheater, and reheater. Flow of water is countercurrent to the flow of the gas. Steam from the superheaters is delivered to the high pressure cylinder of the turbine. After doing its work, it is reheated and sent back to the intermediate pressure cylinder. From there, into the low pressure one, and finally to the condenser. We should also mention the other configuration of boilers used at some AGR units. Boilers were outside the void. This enabled far easier access to the unit. It was historically a newer development, despite the fact that the last reactors used the old serpentine design. Because of the many penetrations control rods need to pass through, there is a possibility of misalignment in case of an earthquake. So in addition to control rods, engineers provided a secondary shutdown system. There are special channels that penetrate the reactor pressure vessel from the bottom, specially made to deliver nitrogen, which has a relatively higher neutron absorption cross-section area. Nitrogen is pumped from facilities underneath the reactor, goes through special channels of the core and enters the area just under the dome of the baffle. Then, it also enters the re-entry paths and efficiently fills the whole reactor. In case that is not enough, some number of those nitrogen channels are provided for boron bit injection. During the time of any emergency or abrupt shutdown, the decay heat boiler is used for some time. The AGR fleet was the most thermally efficient fleet of nuclear reactors ever created, with thermal efficiencies a little over 40%. The AGR helped design other reactors and still provides fascination for many. Over its multiple-decade career, no major incidents happened. Even at the time of making this video, some AGRs are still delivering cheap and clean electricity.